Okay, let's look at some of the ideas of lesson 3.2. I mean, sorry, 2.3 limit laws. So we've discussed already that we can find the values of limits of a function by looking at graphs or tables. So we'll get the visual of analyzing what is the behavior of a function at a certain value. What is happening as the x values approach a certain value, right? That's different than what's the value of the function, right? At a certain point. It's what are we approaching? What does it look like it's getting close to? And so, what do we do if we don't have graphs or tables? Which I know you're thinking, well, we can get those anytime, especially with Desmos, right? With the graphene. We'll look at one of these in a little bit. Um, yeah, I agree. You can get those values from tables and graphs now, so that or tables and graphs because we have access to those tables and graphs so easily now for any complex function or relationship or equation. However, there's so much to learn with understanding how we actually come up with those values from an algebraic perspective. And so to begin, we look at the most basic um, limit results that we have, and this was seen earlier, but the limit of x as x approaches a equals a, and limit of a constant, no matter what x is approaching, is a constant. It's almost so easy that it's complex, right? The limit of x as x approaches equals 2. Again, the reason is this x is the y equals x line. That's the function we're talking about. And so anytime we have a continuous function, we can evaluate a limit just by substituting in the x value that it's approaching, because the left and the right side would be approaching the same value for continuous functions, or anywhere if the function is continuous at that point that you're approaching. So that becomes our quick way of evaluating the limit. And now here, looking at the laws that were introduced in 2.3, there are different rules that help us evaluate limits. So the sums of two functions, the difference of a constant times a function. So when you start to think about it and look at a function like this, you see 4x plus 2, but really it's a combination. If you really think about it, it's a combination of c times x plus the constant 2, right? It is some derivation of one of these forms here in some way. And so then we have rules to help us simplify or evaluate limits when they're roots or powers, or when we have a rational function, or a function where you have a quotient, right? Or we have functions multiplying. So when you think about it and really look at any function like this one here, it's a complex function. However, when you look at this here, you will see it's a combination, it's a quotient. And then even within the quotient, you have a constant times x minus 3. So really these could be simplified into all of these forms here in some way. So it's important to recognize that these functions are really just a form of one of these in some way. All of them are, even though here's a product of two functions, right? And so into its pieces, there's x, there's the quotient. So ultimately, we're breaking it down so I could find, so that I can find the limit right here. We know that's 2, there's 2 and 1, right? And then you have the constant, you can square it. So this is, I think, a really good one to kind of look at the origins of how, or the beginnings of how this applies to this. And then we end up trying to do it faster in algebraic form. And so take a look at this one. This is a good one to kind of analyze and think about. The next thing would be theorem 2.6, the limits of rational functions, right? When you have a polynomial over a polynomial, that becomes an interesting case where we then start to, let me show the solution there. We see, as we look at this here, you can, because when I substitute 3 into here, this, even though this rational function is not continuous, it's continuous at 3. So I can just substitute a value, and that's the key. Even though this is not a continuous function, right? We have an asymptote at 3 when we're checking to see what's the limit as x approaches 3. It's continuous, so I can just substitute my values in there. So it's important to recognize that. And then looking at, we have certain situations, right? So how can we think about, we're still in a rational functions, or when you have a quotient. Sometimes when you substitute, we're really interested in not where it's continuous, that's kind of obvious. We're interested in what happens at these discontinuities, right? Where there's an asymptote or something interesting is going on. And so when we're looking at values that approach, sometimes we end up with what's called an indeterminate form of 0 divided by 0. There is no, you can't put it in the calculator to get an answer. So what happens when you end up with something like that, right? So if you plug 3 into this, the limit of this function, right, as we approach 3, you end up with 0 over 0, which is that indeterminate form. And so what has to happen is we have to rewrite this to something, simplify the expression if possible through factoring is normally the technique we use here. And so you'll see after you go through the steps of factoring, and you may need to review factoring of binomials. After you go through the factoring from here to here, you can then, you have a version now that allows you to substitute 3 in to evaluate the function. Again, it's not really evaluating the function at that point, it's finding the limit. What happens? It allows us now to evaluate what happens as x approaches 3 to this. And so then you end up with a value there. So that's one of the techniques. Another technique that I had shown you in, I think, the other video with square roots. When you get something kind of interesting looking like that, there's a move called the conjugate, multiplying by a conjugate. Especially when you see the square roots, that should be one of your first moves. And what you're doing with a conjugate, it's like a difference of 2 squares. That's what's going on, and that's what allows you to simplify. When you take this times this, and then as you see these 2 pieces, think of this minus 1, the same thing plus 1, it's a difference of 2 squares. So when you multiply it, what's left over is just going to be your x plus 1. Now, when I multiply this and this, I'm left with x plus 2. And then this times this is minus 1. So x plus 2 minus 1. That's where the x minus 1 comes from. Again, this times this is just x plus 2. And then the middle terms cancel out when you expand it out. So once we've done that, then you can again substitute in and get a value of for the limit. Remember, this is not the value of the function. I think here was, again, I showed some of this algebra, the complex in the other video. I shared some of the algebra for this lesson. You then have to rewrite that expression in some way that allows you to simplify. And again, the thing is, there are multiple ways to do it. There's a step skipped here. I would do 2 times 1. I would rewrite this as 1 fraction, and then it helps you identify what you want to multiply to simplify on both sides. But again, as you walk yourself through that, again, another technique that you're expected to know. Here also another, same one there. And so looking at some other expressions. So again, when you plug in 0 here, you get a indeterminate form. And so in this case here, if you get kind of stuck, we have to come up with some other things, and I would add these functions together and then try to evaluate the limit there. So that's stuff I wanted to, again, to highlight. There's a lot of things here. Oh, there's one more here, which is these, if you hear my dog, I apologize. What you hear here is evaluating 2 sides of it. So when the function is, you have a piecewise function, it's another interesting case, and we're really interested in where the pieces come together or don't come together here. So when we look at that there, you will see so these piecewise functions, you can see the graphs going back to graphical. And this is where the graphical representations are important. You can see, trying to evaluate the limits here. You look at the left and right hand side and notice as you approach 2 from the left and right, because they're not approaching each other, the limit doesn't exist. It also shows you it's discontinuous here. But again, you can evaluate them because these functions, again, are continuous as we kind of go through at that point 2. I think there's other, again, forms that you want to be looking at. Again, anytime you have these division by 0 and k is not equal to 0, right? We have some things we need to do. When you plug in 2, you get a what is the behavior, right? What is the behavior you see as you broke up this product here? You can see you end up with a value times negative infinity. And so we would end up with a positive infinity. Again, it's always awesome to, or good to, verify this stuff with the graphs here. Again, to kind of, I want you to read through these if you haven't, or again, go through the right videos to explain that. These are good examples of explaining kind of some of these indeterminate forms. I guess lastly is the squeeze theorem. This is a theoretical kind of conceptual idea, and it's sometimes hard to understand why and how we would apply it. And for sure it's an idea, that sometimes we can't evaluate functions. They're so complex. Again, let's assume without a graph, right? That it's hard to evaluate the limits. However, if we know some function is actually between 2 other functions all the time, and I can evaluate the other functions, then I know the limit of the middle function will be equivalent to those other 2. Now, again, it's in practice hard to think about. But we can see, here's a graph we have here. So we look at it, we have 2 functions. And so this x cosine x, the limit of that, it's kind of tough to see, or to evaluate as x approaches 0, because when you plug it in there, okay, we can take a look at the graph of x cosine x, and then what we try to do in this case is we try to find functions that this is in between. And so this is a classic place to apply the squeeze theorem. Cosine x, we know, is a value between -1 and 1 all the time. So this is a true inequality. And then I could multiply both sides by absolute value of x, right? And remember, when you multiply both sides by the same value, you are not changing your inequality unless it's a negative and then it reverses, but you still have that same. So just multiply both sides by the absolute value of x. And now in the graph here, you see you have absolute value of x, absolute value of negative x, right? You know they touch at 0. And then what we see is we see x cosine x is a graph always in between those 2 graphs. So because that's the case, and we can evaluate the limit as x of this side as x approaches 0. We can evaluate the absolute value of x as x approaches 0 equals 0. We can apply the squeeze theorem and say the limit of x cosine x equals 0 as x approaches 0. We know it because this value, algebraically, we could see is always between these 2. So very, very interesting finding there. And again, it's a theoretical piece, so make